Good afternoon, everyone. Thank you for joining us today for our webinar, Hot Aisle, Cold Aisle Containment, Truth and Consequences. This is Jennifer Beliveau with Triad, and I'll be moderating the presentation. Joining me is Paul Bemis, President and CEO of Applied Math Modeling. Paul brings over 30 years of experience and knowledge to the engineering simulation marketplace through the widespread use of computational fluid dynamics-based modeling in the data center design and analysis market. Gary Meyer is the president of Triad. Gary is an entrepreneur that has developed several businesses focusing on improved airflow dynamics. He has patented several designs that promote passive solutions to improve fluid dynamics as they pertain specifically to airflow disbursement within office space, clean room, and data center ecoclimates. Stephen Howell is the CEO of Technology Connection, a company that is a leader in data center airflow and provides energy-saving solutions to today's complex data center cooling issues. Stephen has an extensive background in providing energy management solutions and has been involved in data center problem solving for over 39 years. We'll be taking questions throughout today's presentation and address at related slide intervals as well as at the end of the presentation if time allows. We will follow up with you after the presentation if we were not able to get to your questions. Please type your questions in using the question panel on the right-hand side of your screen. We are recording today's presentation. If you would like a copy of the presentation, please send me a message through the chat panel also located on the right-hand side of your screen. We also issue certificates of completion for continuing education credit. If you would like a certificate, again, please message me through the chat application and we'll email you a certificate. Let's get started. Paul?
Thank you, Jennifer, and thanks everyone for being here with us today. We have quite a bit of material to go through, and we've got a great panel joining us today. And so we're going to try to move fairly quickly, but we're also going to try to take your questions as we go, as they pertain. We'll also have questions in the end, as Jennifer mentioned. Bathrooms are down the hall to the right for anybody who needs to go, but let me just take a look at the outline here. We're going to take a look at current data center challenges and initiatives. We're going to take a look at existing best practices in containment, some challenges with them, and then talk about virtual containment development. So that's the basic outline. Let's go ahead and get right into it. Data center challenges, I think you all are aware of what's going on here. Essentially, cost of electricity is rising, and it's going to continue to rise, and it's doing it at a nonlinear rate. So data center energy accounts for at least a quarter. Now, that's a good data center with a COP of 4. If it's worse than that, which I've seen a lot of them with a ratio of 1:1 or a COP of 1, then it's almost as much as the amount of power generated to the, delivered to the servers. It's not unusual for me to look at a data center and see that the amount of energy required to cool the data center equals the amount of energy required to drive the servers. And that's an incredibly high amount. It should be more like a quarter, 25%. And also we're seeing increasing costs, over 30% in a 3-year period, and it continues to rise. This is going to continue to be an issue. Also, the environment's getting hotter. We're running into many situations where rejecting heat is just becoming an issue because of hot roofs and density on roofs. So getting the heat out of the data centers is problematic as well. Now, just for completeness, I'm going to talk a little bit here about PUE, just so everybody is sure they understand PUE and what it is, because there is a focus on it. PUE is the total facility energy divided by the IT energy. And this is a metric that is popular in data centers today. The total facility power is everything plus the IT equipment divided by the IT equipment. So if total facility power went to 0, or everything but the IT equipment went to 0, you would have a PUE of 1. But of course, you have to do things like usually run a chiller, you got to run pumps, you've got to have fans, you've got to have a UPS, and you've got to have batteries. So it ends up being, of course, higher than 1. But as it turns out, 75% of the non-IT load is actually related to cooling itself. So the elephant in the room with respect to PUE is cooling and how much energy you deliver to cooling, particularly the chillers themselves. That accounts for a whole bunch of it. And then, of course, the fans. that drive it, and then come the pumps. So it's really 75% of the non-IT load is related to cooling itself. And as a result, it really becomes cooling energy plus IT energy over IT energy. At least that's the dominant component. And focusing on cooling efficiency gives you the biggest payback. It's always great to have more efficient IT servers and more efficient UPSs, of course. But the big one is cooling energy. So if you focus on that and understand how the cooling system works, that's key. Airflow management is the low-hanging fruit. Studies have done, in fact, the DOE did a study back in 2009 suggesting 30% saving by focusing on managing your airflow more effectively. And now popular initiatives to improve it, well, you want to maintain those rack inlets while you do these things. Increase room set point. If you raise the temperature, in particular of the cold air coming into the data center, you'll get roughly 1% per degree F chiller efficiency. Now that's a rule of thumb. It doesn't apply everywhere, but it's a great way to think about it. Ashrae talks about that as 3.5% for every 1.8 degree F. And the curve is fairly flat, so that rule of thumb works fairly well. So rising the set points, which of course stresses the rack inlets, because if you don't do good air management, those start to rise too. The other point is variable speed. Air delivery systems controlled either by pressure or temperature. That's another good way to do it. Fan speed is a second order effect. It's actually cubic. Fan law is cubic with respect to power. So slowing down your fans can save quite a bit of energy in a nonlinear way. And then, of course, going with higher temperatures across your servers. A lot of servers today can handle 30 degrees F across them. Delta T of 20 is conservative. 30 is a little more aggressive, and it drops your supply volume requirement from the cooling units, which allows you to run them a little lower. So that is another popular method. And then, of course, there's hot aisle and cold aisle, and that's kind of the focus of what we're going to be talking about today. Hot aisle containment or cold aisle containment has been used successfully by many, but there's also a little bit of oversubscription of hot aisle and cold aisle, and there are some consequences of hot aisle cold aisle that we want to get into today, and we have some good cases to review that. So let's just take a look at containment examples. Here's one. This is kind of a soft shell containment environment. These are overhead. They often use curtains. They're semi-rigid kinds. They have end curtains. Sometimes they have rigid doors. They clip on. But National Fire Protection is beginning to say, yeah, those aren't really compliant. And a lot of what we talk about today is going to talk about National Fire Protection, because the problem when you start to contain is the fire people get nervous. And they get nervous sort of geographically. In other words, it depends who they are and where they are, or you start to get into some trouble with this. So this is one example that I have found to be popular. Another one is a little more rigid. You top of the cabinet mounted containment, heat shrink, mechanical drops, mechanical apparatus for drop-away panels under heat load. And again, this one is compliant, and it does have the potential benefits of improving the cooling within the rack, eliminating hot spots, and saving energy. So they do work when they are deployed correctly. But meeting that regulation is getting to be very challenging, and retrofitting containment solutions to meet that is expensive. It's also expensive to put these systems in place and to put fire protection in there and smoke suppression with them. And the dynamic infrastructure of today's environments makes it difficult for personnel and to make it tough for people to be in there. Swapping out equipment, particularly in the case where you're a managed environment or a co-location provider or something like that. These containment systems can have some difficulties. Now, here's an example here. I used CoolSim to create some base model examples to show you how these things work. This is an old IBM data center, I believe, that we've used for years, for example, as an example. It's kind of a mess. as you can see. But it's not unusual. It's not atypical. It is 18-inch underfloor. It has cable trays under the floor. It has rack rows pointing in the wrong directions, not in the sense of hot aisle, cold aisle. They actually are pointing out here up at the upper part of this diagram. But they're at 90-degree angles to one another, so they're not lined up in the room perfectly. There's some tape silos over here in the corner, some PDUs. There's gaps between the racks. And this is what we call a naturally convective room. In other words, there's no drop ceiling. There's no containment up to the top of the room at all. It's just what we call naturally convective. Very, very old design in terms of airflow. Now, if we wanted to take a look at that from a CFD point of view and make a run, which I did, you will see that it's not in compliance very well. This particular design is having trouble. This upper right-hand corner, you see we've got issues. We've got issues down here in this corner, and it's because these racks are so close to these crack units that we have trouble. You can see the air starting to have trouble getting up into those corners, the beginnings of those corners. Now, if you look at it from an underfloor point of view and look at path lines, these are path lines of air being delivered by the crack units. That's what these lines are, and they're colored in terms of velocity. And the reason I point this out is really twofold. One, it gives you a good visual indication of what's going on in the room in terms of air travel. Secondly, it gives you a feel for velocity. The velocity here is colored in terms of feet per minute, starting with 0 at the bottom and going up to 1,800 feet per minute as it comes out of those crack units. Now, what's important to note here is that the velocities are fairly high. Many people think there's not a lot of velocity in an underfloor, that it's fairly even, and that's not true to my experience. I find that you have quite a bit of velocity under the floor, and it's going in all kinds of different directions. So the underfloor here is got a lot going on. And I also took the liberty of spinning the model around and taking a shot of the path lines coming out of these floor tiles. And you see here what's happening is they're bending. This is often called the Bernoulli Effect. Bernoulli Effect is as velocity increases, pressure decreases, and vice versa. So we have very high velocity coming out from underneath this crack under the floor, and the velocity is so high and the momentum is so high that the air wants to just continue to travel in this direction, and it doesn't bend to come up into this corner of the cabinet. I've hidden the cabinet faces in this case so that you could see the air coming in underneath that floor. So that's the problem you often have. The air is moving at a high rate of speed. Just because you've put a tile in the floor doesn't mean the air is going to come straight out. It's often going to come out at an angle due to momentum, and it often is going to come out at different rates because of pressure variation. Here we have a higher volume coming out than we have over here due to that pressure variation and speed variation. So that's often what I see when I see tiles close to crack units, particularly these generate 10, 15,000 CFM per unit, and that's a lot of air coming out of those units. Now, there's a couple things you can do. This is an example of a hot aisle containment. And what I chose here to do, when you look at this layout, you want to do hot aisle, I used a ceiling plenum. You can see the ceiling plenum highlighted here in green. It's transparent at the moment. The crack units are attached to the ceiling. This rack row right here lends itself to hot aisle pretty well, so I put a containment around that. This one lends itself as well, so I put containment around that. And here you see I had to build a long wall. This one didn't lend itself very nicely to containment because there's not a row on the other side. So that's really a hard wall going down. Over here it didn't lend itself very well either because the airflow is from the middle to the outside. So I would have had to build a box around this end and then a box around that end. Expensive. So I went with passive chimneys. Just put them in place. And I assumed for this particular run that the passive chimneys were ideal. In other words, they worked perfectly. All the air that came into the rack goes out through the chimney. And you can see even into that case, under those assumptions, by the way, the racks are perfect as well. The racks are on the floor in this model, and there's no gaps in the racks in this model. and you can see that we've still got issues here. This is a compliance plot. This plot is an Ashrae compliance plot, and it suggests that any temperatures above 80.6 are going to be shown in red, and any temperatures below 64.4 are going to be shown in blue. We call these Visine charts sometimes. If any of you are old enough to remember the old get the red out Visine ads, we used to call these Visine charts because it shows red in areas where there's problems. And we've still got issues right there on that leading edge of that incoming air stream, even though we've used full hot aisle containment. And here's a plot as well. This is a top-down plot, temperature here, and you'll notice that there's some leakage going in over this region as well. It's very hot here. The heat is leaking into other sections of the data center because these curtains or partitions are not perfect. I've got them set in this model to leak at 5%. All containment leaks a little, so I have them leaking a little bit here, and you can see it's contaminating the rest of that room. This room is getting up to about 80 degrees over in this section of the room. Now, I also wanted to point out the issue of passive chimneys and leaking rails. Any kind of containment, it's important, very important, to make sure your racks are configured correctly. So I took an example here, and I was showing that inside the rack, I have servers lined up in there, individual servers indicated by color. And then there's a rack rail, you can see it in gray, going around the perimeter. In other words, there's a seal that needs to be kept around those rack servers. The blanking panels must be in place, and the rails between the server itself and the edge of the cabinet and between the bottom of the server and the bottom of the floor need to be sealed tightly because these ceilings tend to be very porous. Ceilings tend to leak badly because there's no specification on ceilings. Unlike structured floor, where the floor tile manufacturer was very careful to try to give you an engineered solution for the floor, the ceiling is often just a drop ceiling, and it's terribly porous. So if you're assuming that this crack unit is going to pull the air from these chimneys through that ceiling plenum by itself due to a pressure variation, you may be misled, because any leakage in the ceiling will diminish the low pressure or make it the same as the room, and suddenly your servers are trying to push up through that chimney. And what happens is they leak. And this is an example of that. This is, I had the rails leaking about 20% in this model. You saw there was already a ceiling grill in the ceiling. The ceiling is not working well. And you can see there's leakage coming around the servers, both around the sides and in particular under the bottom and through the rails and going back into the inlets. The servers are recirculating on themselves inside the rack. This is not unusual, particularly for passive chimneys. You can fix that with active chimneys, put fans in the chimneys, which is a solution that is in the market today. But again, that's more expense. You're adding more cost to it, and you have to worry about failure mode on that unit as well. So this is something we see a lot, and the plot for rack inlets tends to look like this. The racks are out of specification. They're failing the Ashrae standard. Remember, the standard is 80.4. We're well out of spec here. Terrible leakage on the bottom, terrible leakage along the sides. Yet this one over here, which is just a front to back rack with air going up into that ceiling grill, is behaving better. So passive chimneys can have some issues. You have to, and by the way, in any case, whether it's hot aisle, cold aisle, or anything else, making sure your blanking panels are in place, making sure your rack rails are sealed, and making sure there's no leakage across the bottom of these racks is paramount to success in your data centers. So now let's take a look at cold aisle. Same data center, we could have used cold aisle instead of hot aisle. Many people prefer this from a cost point of view because it's just simply easier to deploy. For one thing, you don't have to worry about a ceiling plenum because effectively the room is the return, right? That the cold aisle is sealed, so the hot aisle becomes the room. Now that's hot for people to stand in, but I have seen this done quite a bit because it's generally more cost effective, or at least lower cost, to deploy this kind of solution. Here all I had to do was box in the cold aisle, these two coals. I did have to build a box around this one. This one's not lined up perfectly, so you have to build a box around that particular structure. And this one's lined up pretty good for cold aisle. And the cold aisle performed better in this case. Putting cold aisle in place actually performed a little better, and most notably because it allows the pressure to build and push back into this region a little better. So there's a pressure distribution going on under this floor where most of the pressure was in the center before, and because we boxed in the cold aisle and limited the amount of air that could come into that section, the pressure pushed back into this area and gave us a little better cooling over here. So the cold aisle worked better in this case than the hot aisle. Here's a shot. This is at 6 feet. This is a slice at 6 feet. You can see that room is getting hot. That room is operating at 80, 85 degrees. We've got, in this case, we're using a 60-degree supply air temp. We're assuming a 20-degree delta across the server, so we're running in the 80s on the returns. You can see the cold is leaking a little bit too. These not perfect, so they do leak as they should. About 5%, I think, is where I had them set at. Cold containment is not a perfect seal, so you have to account for that. But this one ended up working a little better in this case. But again, you have to be careful. In this particular variation, I let the servers come up off the floor 3 inches. Just to be sure, the racks on the bottom have to be sealed against the floor, airtight seal. And if they don't, if they leak, this is the kind of thing that happens. We went from a good state to a not so good state here. We've got leakage under those racks. They're beginning to, haven't yet, but are beginning to fall out of spec. As well, the others are beginning to have trouble as well. So any leakage under the racks will cause issues. And if you happen to be in a situation where you've got to move a rack out for some reason, like it's a customer and they want to move it, or you've got to upgrade it with new IT equipment, you have a situation where the air comes out of the back of these servers and in this case is wrapping right back around into the cold aisle. You would think, first blush, that the cold air would push out. But this doesn't have a lot of pressure in it because remember the air going underneath these tiles is traveling at a high speed, and so the pressure in the room is actually higher than the pressure right under that section, and so the air is being sucked back in and it's hot. You can see the temperature of that air is in the 80s and it's being pulled into that cold aisle. And the result is you get something like this, where over in this area you've got a hot air impinging in that cold area, and it's going to reduce the performance and it's going to make these rack inlets in this section fall out of compliance. So one thing about cold aisle containment and hot is you have to be careful during change situations when you're changing equipment and you're changing configurations to ensure that the area remains sealed. Otherwise you're going to run into these kinds of issues. And it becomes a bit of a maintenance issue with respect to ongoing operations to ensure that all of these things stay in the state that they were in when they were first deployed. Not an easy thing to do, particularly if you're a managed environment or a colo environment where things are moving around a lot, and oftentimes you don't even have control of your own equipment. It's owned by somebody else. So we've seen a number of these kinds of situations, Gary and Steve and I, and we wanted to point these out to you. So I'm going to turn it over to Gary here and let him talk about some experiences he has had with the Triad solution and how he got sort of into this situation. Gary?
Okay, thanks, Paul. Some of you may know me. I've been around a lot of years, but in 2003, this all got started with Hewlett-Packard. That's how Triad. They knew me as the raised floor guy because there had been some involvement in a product line we developed for clean room industry prior to that. And so basically they were looking for a panel that would fit anybody's raised floor system, improve the cooling with less energy, and eliminate hot spots. So it became a design question. The solving of fitting any raised floor system was easy. improving the cooling with less energy just became a question of how do we do this in passive. And my background, I'm LEED accredited, and I've worked with the U.S. Green Building Council over the years in underfloor air delivery for office space, and there's a lot of study done on how we transfer heat with less pressure, with less airflow. So that's how Triad started to get designed, and we could tell rapidly we had more than enough cold air, and anybody that's ever just pulled a panel out of a raised floor can tell that. So we came up with a design that treated air and water the same. You basically have to give it shape, you have to tell it where you want it to and at what speed you want it to go. So it became a fluid dynamic discussion. So in designing it, we took those things into account in looking at what can we do to change the delivery point, which is where the airflow panels and the raised floor come into question. There's a lot of other solutions today, in-rack cooling, and all of them have benefits. They all have benefits. It becomes a question of what's the cost to do it, the initial capital costs, and what's the operational costs. So that was our approach. These are some of the panels that are out there today and have been out there. The upper left-hand corner is a standard 25%er. It's been around for 50, 60 years, is pretty much the norm. The panel to the upper right-hand corner is what you see with aluminum graded panels. And basically graded panels have no top plate surface. So they're really not designed for walking surface as much as they are just to let air flow out rapidly. The bottom left-hand corner is one of the newer designs out there that's, again, a graded panel. It does not have a top walking surface. It does shoot a lot of air. It directs it a little more angled towards the face of the server rack. The bottom right-hand corner is a new 25% perf. Doing similar things, it really operates very similarly to the old 25% perf, but they are inexpensive. In the Triad design, we went to one of the parameters is it had to be heel safe and ADA compliant, so we use a top surface on top of our airflow grates. We use varying orifice sizes specifically because we want the air to come out in a certain way. It has the directional anterior fin on the bottom that's curved, so we're collecting different amounts of air based on velocity. Triad is actually designed realizing there is velocity under that floor. We're never going to get it to just be totally stagnant, 100% pressure. So those are kind of the premises of designing the patent of the Triad panels. This is an example. We've spent years trying to get into modeling so they could model our airflow, but because of the calculations based on the type of airflow coming out of Triad, it's totally different than a laminar flow panel, which is what grates do. We went to a turbulent flow because it transfers heat much more effectively than laminar flow. And we had end user after end user testimonies, and this is one of them. To the left-hand picture, you see what it was like before. It had the standard aluminum grate that we showed earlier, fully populated in 2 rows. They put in 4. You can see the 4 blue dots in the center picture there, 4 of the Triad ice flow panels. And that was after 1 minute. You start seeing a change in the temperature readings at the face of the server and at the panel floors themselves, which means even though they're aluminum steel, they should be showing similar temperatures on the metal surfaces themselves. 1 minute later, on the third picture to the right, you can see this flooding effect of a change in temperature, and Triad will drop the temperatures anywhere from 5 to 15 degrees from the bottom of the server and all the way to the top of the server, pretty consistently. And the difference now, the only difference now, was in how the air was flowing out of those airflow panels. So it became this was the fluid dynamic we were looking for. And so that's the effect, that's the foundation of what Triad does. We focus on it passively, and this will go in, Paul will go into more of this. but you'll start to learn more of the difference between the laminar and turbulent flow here.
Thank you, Gary. Yeah, you're right about the laminar versus turbulent. So what happens with laminar flow is it doesn't transfer heat very well. It's well known in fluid dynamics circles. You see this kind of thing being used a lot whenever there's mixing going on. When you're trying to mix or trying to get the flow to transfer heat, you look for turbulence. The turbulent flow actually aggravates the boundary layer of the surfaces that it bumps into and creates a better cooling effect, a better mixing effect. So oftentimes you'll hear people talk about, well, we need more open area out of the floor in order to get more air to satisfy the server. Well, that doesn't always work well, because what happens is the air has momentum and it's coming up at a very high velocity. It's typically laminar. I hear the idea of deep floors, so you get laminar flow, and then the air comes shooting up out of there and goes right by the server. It causes a delta P problem. So I've been in data centers before where there's too much open area. The servers are screaming because they're having to overcome the pressure differential between front and back, and the air is shooting straight up and bouncing off the ceiling and going back to the return units cold, which makes their efficiency worse as well. So this idea of just give me more air doesn't really satisfy the need. What works better, it appears, is to provide the right amount of air with a bit of a spin or some kind of mechanism for creating turbulence. And that seems to work a whole lot better. And as Gary said, in practice that worked. Now, Gary approached us about a year ago to study this in some detail using advanced CFD models. And we created a model of these tiles. We did 3 tiles at first. We did the 56 and the 25, and then of course we did his triad tile. Now here's a shot of just what I was talking about. This one is the typical 56% open flat bottom tile. And look at these path lines. The airflow, by the way, from left to right, as arrows indicate, and in this lower left-hand corner you can see the air coming rushing in and then banging right into that leading edge, this leading edge of material. It's flat. It's there for structural purposes, but it bangs into it, and then the flow separates. You can see over here in this diagram the flow starting to separate right here and then having to go around it. And what happens is it misses because of the fact that it's bouncing and you've got momentum here, very high velocity. It's missing the first few sections of the tile altogether. And then finally it slows down enough and bangs into another one and creates these jets that go straight up into the air. And the result is that you get quite a bit of recirculation. Now if you take a look at the triad tile over here on the right, what Gary has built is a tile that has this underfloor structure that acts as a mechanism. He still has a structural issue on the leading edge, of course, because you really need a structural component there for strength. But he's able to capture that air quicker with these underfloor structures and pull it up into the room and redirect that air up into the room. He's actually capturing it and redirecting it, where the one on the left is missing, and then finally when it does hit a few of these things, you get this this continued tearing effect and really just a poor performance. So if you look at them side by side, you'll notice what's in blue here is recirculation. So these are negative velocity values going back into the tile. And you see that about 20% of that tile under that study, which was done with about 0.05 inches of floor pressure, is recirculating, where you've only got about 3% on the similar ice panel. So the 56%er causes this really high-speed jet to go up. We did a webinar on this earlier. You can go back and look in our archives on the CoolSim website if you'd like to see it in detail. But here's 3 of them side by side. We have over here on the left just the 25%er, which just doesn't really perform well at all. It tends to puddle at the bottom. It diffuses very quickly. It doesn't reach the upper parts of the 7-foot rack very well. Here's the 56%er, jet going straight up into the air, very, very high-speed singular jet going by the rack. This causes all kinds of pressure problems near the rack, particularly at the bottom. And this is the ice panel, the airflow panel that Gary has produced. Notice the plume is larger, it's bigger, it's rounder, it's turbulent, and it gives you a little bit of somewhere in between the other two. It gives you good momentum, so it reaches the upper region of the rack without shooting so high that it tends to cool off the return temperatures of the cooling units. There are a couple of new variations that are on the market. This one we studied in detail as well. This one has fins on top. This is called a grate bar tile. It's got the fins on top, but none under the bottom. So again, it's much like the 56%er, except that it has a stringer that goes right across the middle. I'll show you in some detail. Well, you can see it in the upper left-hand corner. The stringer that goes across the middle there, I suspect for strength, is causing a massive separation in the flow coming out of it, and this one is actually worse than the 56%er according to the work that we did on it. Close-up here shows that. Here's again the air from left to right, hits that first piece, separates badly, misses almost a third of the tile. Then it finally hits that center stringer and separates again, so there's a gap there in the middle, and then you get some movement over here. Over on the right, again, the same conditions for the triad tile. It's just behaving better. It's catching the edge quicker after the separation, getting redirected up into the room. So if you take a look at those two side by side, again, same conditions. We've got almost a third of the floor there. 28% is being recirculated onto itself. That means if you were to take a piece of a paper and laid it near the floor there, it would be sucked back down onto the floor right there. So yeah, it looked like audio dropped out there for a moment. I'm sorry. We do have lost the feed. No, that was on my end. Yeah, so sorry, folks. Internet's not perfect. Let me just back up there again, and I'll show you this one again. This is one of the newer designs. This is called a grate bar. And you see a big separation here. The flow bounces off that first edge, separates badly, slows down, hits the center finally, separates again, and then continues. The slotted tile, the ice tile from Triad just does a nicer job altogether. And if you take a look at recirculation here again, plot of recirculation, you see that nearly a third of that tile is being recirculated. In other words, the air is going down into the floor here instead of coming out. If you were to take a piece of paper and lay it on this edge of the floor, it would be sucked down. It wouldn't come up. Where over here, you're only seeing it at 3%. Same exact operating conditions for both of those. So what I did is then I took the Triad airflow panels and I put them back into the data center that I had modeled earlier. And I took out the 25%ers and replaced them with triads. I staggered them and only used 99 of them compared to 144 that were there before. So I dropped by roughly a third the number of tiles used. Same operating conditions, all cracks are on. The balance in this room is pretty close. In other words, supply air volume is matching what is required by the racks pretty well, or the RCI is nearly 100%, RTI is nearly 100%. The supply air temperature about 60 degrees Fahrenheit, supply air temp, same as before. I did close the big gaps between those racks at one end, fairly simple. No physical containment used. I did seal the rails, and I have no gaps under the rack. And let's take a look at how it performed. First, I want to show this slide. I wanted to show you the between the racks. I did put some physical barrier just to seal those big gaps, which was kind of obvious and evident. The only thing I did, however, except for put the triad tiles in, and there's the results. Now that's pretty good performance right there, considering there's no physical containment. Remember, originally we had bad performance over in this part of the room. That was causing issue. We had bad performance in this part of the room. So here we are with a third less tiles, but a different design. These have the triad design, the underfloor structure, and if you put them side by side and you take a look at that cold aisle design originally compared to the no containment design, but with the Triad panels, you see that they are doing a very good job considering the amount of money we saved by going with the solution on the right. So you can get close to our experience here, and Steve is going to go into this in more detail in a moment, but our experience here is so far that you can get near the cold aisle kind of contained performance without having to put the physical structure in place. So I'd like to go ahead and turn it all over to Steve and let him share some of his experience with us in this area. Steve?
Yeah, thanks, Paul. So kind of how we got started on the development of the virtual containment really started with a couple clients of ours. One, he'd given us a call a couple of years ago and indicated that apparently the city had changed fire marshals, and the new marshal, so to speak, was in town and came over to the data center and did an inspection and said basically they're not within code. And so the customer's a little panicked, was looking for some help. So we went out there, spent some time in the site. What actually ended up happening is we removed all of the physical containment. We had two other clients that, and let me also say that we had met these clients after they had purchased containment from someone else, so we got involved a little bit later. But there ended up being two more clients that had the same situation, and they were really looking for some help. You know, what can be done? Obviously containment works. We know it works very well. We're having a lot of problems now with fire code issues, and we're looking for another solution. So that was in early 2014, which kind of lined up with the new NFPA regulations, National Fire Folks regulations, and it's Regulations 75 and 76, which relates to data center fire protection issues, and then also telecommunications fire code issues. So in looking at this, we started talking to clients and we started asking them a lot of questions. What were the problems? What were some of the issues they were seeing? And one of the big things that came out of that was that, listen, we have this big physical infrastructure and it works really well until we have to try to make a change. And as soon as we try to make a change, such as bring in a different size server rack, or we need to remove a server rack, or if we're going to be, combining data centers, what do we do? We've got a problem with we have a challenge with the room. We have a challenge with the void now that's been put in place, and so we've got this major problem, and we end up with these voids. We spend all this money, and all of our energy has been lost. So essentially, we looked for an answer to try to come up with something a little better. And we started talking with the Triad back at that time and started talking about their turbulent flow technology and how that all works. I also challenged the team to come up with ways to, try to come up with a way to eliminate completely the physical nature of the structure. So, understanding about 90% of the existing data centers were on a raised floor. We started development in Q1 of 2014. We're really focused on trying to limit the physical components of the containment, and came out with, what is now the new containment development. Next, please. Mm-hmm. Next, please. Thank you. So essentially what we did is we came up with a practice that utilizes a combination of static pressure balancing and turbulent airflow technology. And we talk about static pressure balancing, and one of the things that Paul talked a lot about was, velocity of the subflow, or the speed in which that air is traveling. We have some unique proprietary methods of strategically slowing that air down if we need to, which also just helps dramatically with the technology of the tile itself, which is the turbulent flow. So it actually, as he showed you on some of the earlier slides, instead of missing, so to speak, maybe those first 2 or 3 small areas of the tile, we can get more of that efficiency up through the tile. As a result of that, what we found is that as Gary had mentioned early on, it's not unusual to have the temperature at the 6-foot level the same as the actual delivery temperature. Matter of fact, we've seen that in the last 3 implementations we've done. So it's a structuralist system. It's based on science analytical properties, which eliminates the need to build a room. And essentially what it is comprised of are tiles. It's an assessment. It's tiles, the triad tiles, and airflow balancing. Knowing where to put those tiles, understanding how the air is traveling under the subfloor, understanding the heat load, we're able to basically create a virtual containment or containment-like condition that is working very well. Next, okay. So existing, I'm sorry, I think I jumped forward one too many.
Oops, I'm sorry. There you go.
Okay. So existing data center containment practices, just kind of a quick overview, quick review. Efficiency gains, to be had through proper cold air separation. We know they work. We know they work really well. We know some of them don't meet the NFPA standard. We know that as data centers become much more dynamic, there are some difficulties in maintaining the integrity of the containment, and some of those investment dollars that were spent trying to contain the air has now been lost. As a summary, under the structuralist containment practices, we don't have any concerns with NFPA requirements because it's just simply an arrangement of tiles. The ability to evolve and change with the dynamic data center environments, there's no issue there because we can actually remove, in our test, you can actually remove server cabinets. We've measured this. We've actually shot it with a thermal gun, and you can look down that cold aisle, and the heat, none of the heat from the outside back sides of those server racks will wrap around and enter back into that cold aisle. So all you'll see is one big wall of cold air. So rather you have, all of the server racks tight, or you don't, or you have half of them missing, or they're different sizes. It has little to no impact on the way that those cold outs are cooled.
Steve, one question I have for you just in this area. Do you find quite a bit of variation with respect to fire marshals and their agreement on what works and what's acceptable and what's not acceptable?
Well, yeah, I kind of call it the wild, wild west.
Yeah.
We see everything.
Yeah.
We 1 week we're out in California, and there's one city where a fire marshal is very stringent. Then we're in another city, and the fire marshal doesn't pay much attention to it. But I think what's probably, it seems as though we're finding more and more change in that area. We're finding, I think, the national, well, they're trying to. I think it's going to take a while, but I think the eventuality of it is that, we're going to have more governance when it comes to data center containment.
Yeah.
And the downside of that is what we've learned from these clients we worked with is that when the city gets involved, you have to pull a permit. And in order to pull a permit, you have to have an architectural firm involved. And when you get an architectural firm involved, you have to get a general contractor involved. And so all of those things are exponentially more expensive than the actual solution in some cases. Yeah. So that's something that we have run into. So I have a couple case studies I want to share with you. 1,500 square foot site on a raised floor. You can kind of see this information. They had a couple of 20-ton units. They actually had their initiatives where they only had 2 units, but they were thinking, that it was a very, very small room. They're thinking they're overcooling it, yet they still had hot spots and really didn't know what to do. So we basically deployed Samurai Containment. Next, please. And in this particular room, this case study model, you'll see on the left side under current conditions, they actually had 1 cold aisle with physical containment. There were 9 just standard 25% tiles in that cold aisle, and it wasn't installed properly. And you can see it's fairly blue, which means blue is cold, and as the numbers head towards red, it's warmer. But that very first area where the arrow is pointing, you'll see it's somewhat light blue. After we installed the containment, the structureless containment, we actually turned off one of the units, which was one of their goals because they wanted it to be N+1, and we cycled it off. And you'll actually notice that we still remained very cool in that same cold aisle. As a matter of fact, if you go to the next page, if you look at the vented tile production, they were producing about 20,000, just over 20,000 CFM of air through those tiles. Of course, we turned the unit off, so that dropped almost by 50%. But interestingly enough, the inlet temperature only went up like 0.8 to 0.7 degrees. So it, almost no change to the air temperature. Static pressure dropped to less than half, and and you see the annual cooling reduction in savings that was provided for these folks. And this particular site was in a remote part of Texas where their energy cost was about 5 cents a kW. So they still saw a very substantial payback. One other comment I'd like to make on the static pressure is that this triad tile, and Gary had stated this, and we agree, it's proven itself, it does not require nearly the amount of static pressure that the other tiles do to produce the type of cooling capacity that it does. So again, the science is incredible, and it works very, very well. So this was case 1 results.
Yep.
Case 2 was a little bit larger center, just over 10,000 square feet. They had 9 30-ton units there. This site had rigid containment, and the issue they had is they were going to start bringing in servers from other locations. They were trying to consolidate, downsize, etc. And so their rigid containment just wasn't going to serve them well for that change. So they contracted with us, and again, we deployed Samurai Containment. And if we go to the next slide, and the case study model 2, it's obviously a lot more going on. It's a much larger site under current conditions. They had some gaps and voids inside the rows that were due to the dynamic changes, so they had removed some racks and redeployed them. They'd brought in some racks that were a tad shorter, so they were losing some of the benefits of the hard containment. As you look at on the right side under installation results, which we put in the structuralist containment, we actually eliminated all of the critical hot spots inside the cold house completely. Because again, we are concerned about voids. We aren't concerned about missing racks, etc. Mm-hmm. So those are results on case 2. And then as we begin to look at the vented tile production, again, they were getting about 170,000 CFM out of the tiles collectively. We actually were able to get at some of that stranded air, and so we actually improved that to about 181,000 CFM. You'll notice the inlet temperature is down, almost 7 degrees, and by the way, didn't change set points on anything. Static pressure remained relatively the same, went down a little bit, but in this particular case, they saw a chilled water savings of 36,420. Well, they didn't turn down the crack unit or turn up the crack unit set points. They actually started dialing up the set points on the chiller plant, the water delivery set points on the chiller plant. Mm-hmm. So you have two types of savings. You have the annual chilled water savings, and then in this case, we had the IT consumption savings, and we attribute that to the fan curve. Mm-hmm. Because we cooled the variable speed fans in those servers just by cooling the air. Obviously there's a little bit of savings there. And by the way, these numbers came right from the customer. The financial numbers came right from the customer. So they provided that back to us, which was very nice of them, and so it gave them a payback of about 20 months.
Interesting point there you make about servers. When I was young, we were all one speed. Now they're variable speed, and they seem to kick in about 77 degrees. They start to go into overdrive. And I don't think that overdrive is linear. It seems like they just, whack it really hard and drive those up. And I've been in many data centers where those fans are screaming because they're not getting either enough air or the inlet temps are too hot. So we often overlook the fan speed on those IT machines. In fact, in the PUE calculation, you notice that IT power includes the fan, which isn't really very accurate.
Right.
But yeah, that's an important component. Thanks.
And many of the servers now have up to 3 fans in a tray, mm-hmm. And I do know that they operate based on the speed the air is traveling and the temperature of the air.
Right.
So those two factors are very important. So the future of the technology, we're in the process of developing a top-down plenum solution. Obviously, this solution currently is just for a raised floor, but we're actually working on this. It's not coming along as fast as I wanted it to, and it's really my fault. But essentially, we think that we'll be able to use the same type of technology in top-down applications for not only inside data centers, but just inside of any facility that is providing air through the ceiling. But again, that's stay tuned. That'll be coming soon. We have had requests for that already to try to get spec'd into some new builds, but we're just not there yet. That was really all I had. Paul, I'm going to give it back to you.
Okay, thank you. I've just got to quickly summarize. We want to take a lot of questions. I think we've had a number of them piling up. Jennifer will be handling the questions and feeding them to us for us to respond to. But let me just close by saying that what you've heard is that it's not a one-size-fits-all kind of thing with respect to containment. There are things that can be done as you have seen to take you a long way towards the performance of something like a cold aisle or a hot aisle contained solution without having to give up your flexibility, give up your fire protection issues or face them, and pay the prices associated with that physical infrastructure. There are emerging technologies that get very, very close without the need for physical containment. So this kind of thing is going to continue. It's going to evolve, and we wanted to bring it to you, show it to you, show you some of these enhancements. Together with Steve, we're able to show you some case studies that are proving it, and we wanted to make sure you're aware of it. Now, we're available here. It's a little before the hour. We've got some questions, I think, Jennifer, that you might like to pass over to us.
Sure. You guys ready? We do have a few questions. Thank you, everyone that submitted the questions for us. So for those of you that reached out to me for a copy of the presentation and a certificate, we'll get right on top of that after today's webinar. So the first question, and actually this is from the same attendee, so they're related in nature. One of them is, what differences would be observed between modeling cracks with older fans in turning vanes versus newer EC plug fans under the floor, especially velocities and Bernoulli Effect?
Well, there is some effect. It depends on whose fan it is. For example, Stoltz doesn't drop their EC fans down into the floor, and Liebert does. So it does depend. If the fan is under the floor, you get more of a radial throw. In other words, it's throwing horizontally further and faster. That can be good and it can be bad. If your tiles are near the crack, it's bad. But if you're trying to get air across to the other side of the room, then it's good. The EC fans don't have as much pressure. They tend to roll off, the EC fans roll off quicker in terms of delta P. So where you can get a couple of inches of pressure, a couple of inches of water, delta P across a radial fan, the axial fans don't do it quite as well, or the EC fans. So they're lower. They don't have as much pressure differential. They are more efficient, and you can control them better. So essentially, everybody's going with EC fan now. If they're in the unit and it's blowing straight down, there's not much difference compared to a normal downflow unit using the older style fans. But it is situation dependent, as many things are, and it pays to model it and find out. That would be, of course, my advice. Jen?
All right. And then, Paul, what kilowatt load per rack did you use in your model that you reviewed?
They were running around 6. They did vary. That's an older model that we've had for a while. They ran in the range of 6 to 8. If I remember correctly. I'd have to go back and look in detail, but that's what I remember. They weren't more than 10 from what I remember. Okay.
All right. Yeah, and then another bit of feedback. In my point of view, hot aisle containment cannot be done with perimeter cooling. The right solution is with in-row cooling. Don't you agree?
Not necessarily. In-row is its own sort of set of issues. Remember that with in-row cooling, you've got the air going absolutely parallel in a different direction than what the fan in the rack wants it to go in. So in-row has its own set of issues. It takes up white space. There's an N+1 situation that you have to be very sensitive to when studying failure mode analysis for in-row. And I have seen perimeter work very, very well in hot air. Jennifer, you and I both visited a customer that we have who was using down row perimeter cooling and getting PUEs of about 1.3 using hot aisle containment. And they were simply putting plexiglass on the end of the aisles and letting the air naturally float up into the ceiling and doing a very nice job that way. So I have seen perimeter cooling. I wouldn't draw any hard lines in the sand and say that you must always use this for hot aisle or whatever. I have seen some pretty creative solutions, and each one is somewhat unique, I suppose.
All right, then what about cold aisle containment servers being less than 64 degrees Fahrenheit?
Well, I mean, it's not going to hurt the server to be cold, of course, but you're wasting energy if you're driving it lower than that. I mean, right? Now, let me be specific. There are cases where you have cold air because you're using a free air system, or you're getting cold air really cheap somehow, like pumping it out of the ground. I've seen that used. We have one customer who's got an aquifer under the ground, and they just have to circulate water and blow air over a fan coil, and they've got all the cold air they want. Now, what's interesting about this is, again, if you go back to a tile that's got turbulent flow coming out of it, you can take that very cold air, dump it into the cold aisle at a very low volume, and as long as it's spinning and twirling, it'll mix with the warm air going in the room, sometimes around the rack, and provide you sufficient cooling at very low CFM. In other words, cold is not bad. You can use it, and if you use it together with some turbulent flow technology, it can be a real benefit. But I think the question dealt with what happens when they're cold. Well, they're out of spec, but it doesn't really hurt them. It's just kind of a waste of energy.
All right. And then is the airflow modeling data based on no materials in the plenum, such as, cabling and all the other good things we find under the floor?
Well, you can always model the junk in the floor. It's just a matter of trying to characterize and put it in there. In the model I had, there were underfloor cable trays, which weren't porous in the case I was using. So they could be cables, they could be blocks, they could be pipes. You can put it all under the floor and model it that way. It's not a problem. It's just an issue of knowing where it is and putting it in there. And it also relates to what your goal is. If your goal is to just try to figure out in general what's going on, then the less detail the better, because the model will run faster and be smaller and be more versatile. But if you are having some issues and you want to get the detail up, then you need to start to model the detail under the floor. You need to model the tiles more effectively. You need to get into the racks and model the servers and where the heat is in the rack, etc. So level of detail is all correlated to what are you trying to get out of the model, or what are you trying to get out of the exercise. If it is to prove something that's fairly straightforward, it doesn't take a lot of detail. If you've got some corner cases where you're really trying to figure out what's going on, then you'll want to add the detail.
All right. We were talking about fire suppression system problems with containment systems. What type of fire suppression did you have in mind?
I think that would probably go to you, Steve. You know more about fire suppression than I do.
Yeah, well, I guess the fire suppression in these three cases that had to do with the location of one of the cases actually had water. They had water sprinkler heads above, and there has to be a specific distance from the water heads in every direction, both vertically and horizontally. In both of the other two cases, you're talking more like a halon or the new technology in chemical dispersion, where you actually have a head up in the ceiling, and you have similar problems with those. And I can tell you that there's a lot of information online on NFPA, but I can tell you their general rule of thumb seems to be, if you're going to put up containment, it has to be somehow connected to the early warning fire alert system that also varies from site to site, so that those panels will release somehow well before an incident occurs. And that is where the issue is coming into play with the architects and the cities, because they're saying, wait a minute, if we're going to start dropping something from a ceiling, before we start dropping things, we better understand how we're going to connect that, and we want to have some governance over that. I think that's kind of where that's coming from.
Okay. All right, how many kilowatts per rack could you handle with the structureless containment?
I'm sorry, could you repeat the question?
She's asking.
Sure.
Yeah, go ahead.
How many kilowatts per cabinet could you handle with the structureless containment?
So that is going to vary from site to site, and let me tell you why that is. You know, we've in all the tests and all the sites we've been in, no two sites are the same. The air doesn't travel the same. The plenum depth isn't the same. The crack units or the cray units or whatever's delivering, the temperature there isn't the same. So there's no way to answer that short of doing an assessment. And in other words, we come in, we do an assessment of what the air is doing in the room, and that's all documented. And essentially, like Paul would say, then some form of a CFD model is done. We happen to have some intellectual properties that we put overlay that then tells us exactly what we need to do. So as an example, one site that we did in California, it was about a 7,000 square foot site, which isn't documented here. In that particular site, we used a lot of their existing tiles, but we actually had about 4 of the variations of the triad tiles in each aisle in that particular case. In the second case, we had about, the aisles were bigger, so we had about 1 tile for every, on average, but it's never the same, on average about 1 for about every 3 racks. And they were running, those racks were about 5 kW per rack. But again, I would hate to say there's a average, because it's different in every single case.
Gary, do you have any comments about that? What have you seen with respect to kilowatts per rack using the triad tile? I mean, there was always this thought, or I've heard people say that, you know, you cannot cool more than, you know, give me a number, 10 kW without going to some kind of containment or rear door heat exchanger, you know, kind of thing. I'm not so sure anymore. It seems to me that you're doing a pretty good job without having to go to those more expensive solutions. Do you have any insight here?
Yeah, we have wide experience in been involved in several studies with National Science Foundation as well. And we at 0.03 to 0.04 static pressure, about 900 CFM. There have been ratings of 17 kW. We've had some facilities that are going up to 30 kW. And it becomes a question, as Steve's talking about, a deployment and a modeling study to really start to understand what the flow turbulent flow works. And there's no gray area in my mind about that at all. That is the preferred science of how the air is flowing out of those panels. And then it's a matter of positioning and understanding the dynamics of the flow underneath coming to those tiles, which is basically coming from any one of 4 directions almost at all times. So it's case by case, like both of you are saying, but we have experience where we've gone to much higher kW with passive flow.
Yeah, that's a feeling I get as well. Okay, Jen?
All right, let's see. Any changes in the cable trays below the floor could ruin the cold air wall, right?
Yeah, oh yeah, cable trays can mess all kinds of things up because they cause pressure variations. Now, as Steve pointed out, they can also help, because if you've got a very high speed flow coming out of a crack right next to some tiles that you're trying to get some air out of, breaking down the velocity, remember that that dynamic pressure, you know, dynamic air, fast-moving air, tends to cause a low-pressure area, right? That's the Bernoulli effect. So what you are trying to do is increase the pressure by decreasing the velocity. So if you drop the velocity by blocking the air, it actually bangs into a plate or bangs into a tray. It can often break down that velocity and give you more pressure. But it can also starve an area for air as well. So, you know, there's a balance here that we have to strike, and it's situational dependent, but in general, velocity is in an underfloor is a bad thing, and by the way, you can't get away from it. I have never seen a data center with no velocity under the floor. So people who think they can drop a tile in, and just because there's pressure under there, the air is going to come straight out of the tile, will be surprised when they drop a tile in, and the air is moving from off to one side, or there's a short cycling on one side, because in particular, flat bottom tiles don't give you any directional control whatsoever. Next.
All right. Could you nominate a reasonable cold aisle velocity?
No. I mean, it's hard to it's hard to come up with broad statements, as Steve had pointed out, that say, thou must do this, or, someone asked me recently, what's the minimum velocity across the front of a server before you have to worry about the delta P? Well, it depends on a lot of things, right? Depends on the server. Depends on what else is in the room. How wide is the aisle? So it's hard to come up with a single rule that says, the minimum air velocity in a cold aisle should be this. Depends on what the servers are, how much they're requiring, how tall they are, where the load is. Is it uniformly distributed, or is it near the top, or is it near the bottom? So yeah, it depends, I'm afraid.
Yeah. I was on a site recently, just an example, that was using the 65% tiles, and they had the whole room full of them, and they had very little static pressure. So in one aisle, you had air coming out at average 900 to 1,000 CFM. In the next aisle, we had negative airflow.
Yes.
But again, the thought process there was more is better, so we'll put in more tiles, and we'll have put in larger openings. And unfortunately, they had some significant problems. Like in anything, if the proper assessment's done up front, then it answers all those questions.
Yes. If there's one universal point I can make, because I know people like to cling to universal points, one universal point, more is not better. Punching a hole in the floor, think of your raised floor as a balloon, and you're just trying to control the air coming out of it, so you don't want to punch a big hole in it. Bigger is not better. It makes the fans work much, much harder to keep the pressure where it is. If you put a VFD in place to control it, the fans are going to be running full tilt trying to keep up. Furthermore, the air shoots by the racks, goes up, bounces off the ceiling, goes back to the cooling unit, cools off the return temps of the cooling unit, drops your thermal efficiency of your heat rejection system tremendously. Remember that the return air temperature is what gives you good cooling efficiency. You want a high return air temperature, and it's not linear. It is a nonlinear relationship. I plotted one recently and found that they're very, very sensitive to return air temperature. You want to keep your return air temps as high as you can possibly get them to get good efficiency out of your heat rejection system. You don't do that by putting in a room full of a high percent area open tiles. And by the way, percent open area doesn't really tell you much, except it's a big hole. What you're more interested in is, does the air coming out of that tile create enough turbulence? Do I get enough air and enough mixing to be able to cool the area only in front of the server rack? That's what I'm interested in, only what's there. So more is not better, usually. Okay.
All right, we are at about 1:15, and we do have a few more questions left, but I'm not sure how long it's going to take to address. So I believe on behalf of myself and today's presenters, we're going to wrap up, and we thank you again for your interest and time with us today, and we'll answer those questions individually. Thanks for attending.
Thanks, everyone. Have a good day.
Thank you.